So you've seen how an unbalanced torque leads to rotation. All right, so if we put 2 kilogram here, 1 kilogram here, meter stick on the center, this is clearly going to do this. It's going to rotate clockwise because this torque overpowers this torque. And what we want to do is we want to be able to quantify that. So what we're going to get into is the second law. The second law for rotation. Well, let's just write out the second law for translational motion. Sigma F equals ma. Net force causes the mass to accelerate. Well, what we're going to consider now for rotation is the net torque. The net torque, if it's not zero, you're going to get rotation. So what we have here is sigma tau equals I times alpha. Now that's something we saw in kinematics. Alpha, that is your angular acceleration in radians per second squared. Sigma tau is the net torque. Now it's not zero. If it is zero, you get an alpha of zero. You get no angular acceleration. And this right here, this is called the moment of inertia. So that's a term that, for the most part, I'd say we always said, oh, you think about inertia, think about mass. Now you can't do that anymore because this is something different. If you remember, I gave you the metal beams. I said rotate them about a specific point, and you're going to find it's more difficult to go about certain points. This is where this idea of I comes in. So now we're going to have non-zero values of net torque, and that's going to result in alpha. And how much acceleration? Well, that's going to depend on how much resistance to motion that we get. So we got to talk about what moment of inertia is. We're going to be able to quantify this. And basically, the first thing I want to introduce to you is the idea of, let's say we have a long, thin rod, and we put a single mass of M on the end of it. So, this could be some sturdy material, like maybe like a piece of wood or something like that, but you got a mass that's much heavier than the rod itself. So we really ignore the mass here. And this is what we call a point mass. This would be a single point mass. And then let's say that, we tried to just take that point mass and kind of rotate it like that. Basically what we're doing is we're defining this as our pivot point. And what I'm going to call this distance here is R. So if you want the moment of inertia for a point mass, it's equal to mr squared. So it's a function of not only the mass, but how far away from the pivot point it is as well. And that's going to determine how much angular acceleration you would get. Let's just say that for the sake of argument, we just tethered this to some sort of axle so it could swing down. It could rotate like a pendulum back and forth and back and forth. If we're releasing it from rest at this point here, you would have a force of gravity here equal to mg. And that would generate torque. There's your distance r. And what would end up happening is that this thing would start to rotate this way. And basically, your sigma tau would be equal to mg, that force, times r. And then basically, you could then calculate the angular acceleration if you know I. Well, here we know I, because I is equal to mr squared. And what happens here? Few things are canceling out here, and it looks like alpha would end up being equal to g over r in this particular case. And that's for only that one instant in time, because if this is actually a much more complicated scenario here, because the second you go like this, your force of gravity is still down like this. And what's going to end up happening is that you're going to get a different torque entirely there. So the value of alpha would actually be pretty complicated through this motion, but looking at that one instant in time, you can see why it would rotate. Now, we can have, obviously, an object that's much more complicated than this right here. That was a single point mass. We can do multiple point masses if we want to. So, if you take a look at, let's say, a baton. Again, a long, thin rod here. But now we're going to say it's got 2m here and m here. And you can rotate this a few different ways. Just like we did in class with that beam, you could choose to grab it there, try to rotate it like this. You could choose to grab it here, try to rotate it like this. You could grab it in the center, rotate it like this. They're all different. So how you define your pivot point is going to really matter here. Let's do this. Let's say that this is our pivot. We're going to grab it in the center and do a 180 rotation here. Let's, for the sake of argument, we'll call this distance R. Now, since that's dead center, this is R as well. And the way you calculate moment of inertia for multiple point mass is this. You simply sum up all your point mass. It's mr squared plus mr squared. And there may be different r's. It's entirely possible that they have different values of r's here. And if you have a third, mr squared, and so on. So if I was doing the I value, choosing this center, this blue dot as my pivot point here, I would be equal to mr squared plus 2mr squared for a grand total of 3mr squared. What if I change the pivot point? I think what you noticed with the beam was that grabbing in the center was the easiest. What if I make it here? Basically, you got the heaviest mass as far away as possible. We've already defined this distance as r, so this would be a distance of 2r. If that's my pivot point, well, this first mast here, it's right on top of the pivot point. So no inertia from that mast there. But the 2m, that's a distance of 2r away, and then we square that. So what's that going to be? Looks like 8mr squared. Much larger moment of inertia if you try and rotate it about that pivot point. You can do the same thing here and see if it gets easier or harder relative to the other two. Alright, so I'll make that my pivot point green. Now this one is a distance of 2r away. Square it. The 2m right on top. So nothing there. And what do we get? We get 4mr squared. So it turns out that grabbing this particular object in the center is the easiest. Now what I've given you here is linear objects, but they don't have to be linear. You can easily do an object like this, and you don't have to worry about direction here. You have to worry about distance from the pivot point. Basically, if we make this one a pivot point, you sum them up, we call this R, 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 R. This would be an I of mr squared plus mr squared plus mr squared plus mr squared, 4mr squared. So that's going to be how you do point masses. There's a difference between point masses and shapes, which I think I'm going to make another video because we're approaching the 8-minute mark. So let me hit stop here.